Now that we've gone through the designs for flops and latches, let's go through the sequencing methods for how we actually use these along with combinational logic. So you can see off to the right here, there's a diagram that shows three different ways of using flip-flops and latches to do sequencing of our logic. So in the top one here, we have two flops, and in between the two flops we have some combinational logic which will perform the logic that we want. When clock goes high, the latch on the flop on the left will capture a new value. That new value will go into our combinational logic, and that combinational logic could take maybe half of the clock cycle, or it could take 80–90% of the clock cycle, but we need to make sure that it takes less than a full clock cycle to get a stable value at the input to the following flop on the right. As long as it does, then the next time the clock goes from low to high for the next clock period, it will capture the value that the combinational logic is sitting there stable, waiting for the flop to capture the value. And when it captures a new value, it will send that value down to its receiving logic, but the flop on the left-hand side will also capture a new value and start a new value of combinational logic evaluating, and that just continues cycle after cycle. Now, by contrast, the next set is what's called a latch design, so a two-phase transparent latch design. In this type of design, we have the input on the far left is a phase 1 latch, and on the far right is a phase 1 latch, but in between we have a phase 2 latch that captures when the clock goes low or when the phase 2 clock goes high. And in between the latches we have combinational logic, but each of the combinational logic cones needs to, instead of being a cycle long of delay, it needs to be only half a cycle. So we need to break up our combinational logic into half cycle chunks. And the way this works is when the phase 1 clock goes high, it will capture a value that will go through the combinational logic. The phase 1 clock goes low, so that value will stabilize before the phase 2 clock goes high. And so we make sure that the combinational logic is a short enough logic path that that value becomes stable before the phase 2 clock goes high. When the phase 2 clock goes high, it will allow that value to go through the phase 2 clock, and then it will start going through the second half cycle of combinational logic. And eventually we want the phase 2 clock to go low so that that value of combinational logic will stay stable when phase 1 goes high again. And again, once phase 1 goes high, we're going to repeat that combination and make sure that we get a group of half cycle worth of logic done for each latch and keep it stable while that latch is open in order to do the next set of combinational logic and keep propagating these waves downstream. Finally, the last one at the bottom there is showing how you can use latches to kind of perform the same functional performance or same functional logic as what a flop does. So if you, instead of using a normal two-phase clock to go into a latch, if you send a clock that's a short pulse clock into a latch, it functionally behaves kind of like a master-slave flop does. And that's because when the clock goes high, the latch will open and allow a value in, and if you, after that value gets in, you immediately force the clock back low, it will now hold that value stable for the rest of the cycle, as long as the clock stays low. So functionally, if you send in this pulse, it looks like it's behaving the same way as a flop does, because it captures a value on clock going high and it holds it almost immediately thereafter until the next cycle. And so this can be a way, sometimes people will use pulsed latches instead of flops because latches have less delay through them, they have less gates inside of them, and so they take up less area. There are downsides to this as well, and we'll go into that a little bit more in upcoming foils. Okay, now we get into some fun stuff, and some of the hardest things that we have to do when we're talking integrated circuits and combinational logic and flops and basically figuring out the timing and just how fast you can run your clock when you have all these flops and combination and latches and combinational logic in your circuits. So there's many different timing delay elements and delay times that you have to concern yourself with. So one of those, let's go through a number of different types of delay that we have to concern ourselves with from a standpoint of looking at combinational logic versus flops versus latches. So in combinational logic, it's maybe the easiest thing to look at. We have what we've called in the past a logic propagation delay. That's the longest amount of time it takes to get a signal when a signal at the input of the combinational logic changes till the output becomes stable again. So the T propagation delay, if you look at the top of the top two graphs there, where A seems to be, you have kind of the X there, it's saying you can either start with a 1 and go down to a 0, or start with a 0 and go up to a 1. Either way, where the 50% switching point is where our time starts, and we want to know what the latest amount of time, so you can see the arrow, line and arrow for T propagation delay is the longest amount of time it takes for the output value Y to switch either from a 0 to a 1 or a 1 to a 0. Then there's also, as we've talked about before, the combinational logic contamination delay. This is the shortest amount of time it can take to get through the logic. And so there's an arrow from when A switches to when the output switches, and that is a lot earlier than the propagation delay. And we've seen in the past that our combinational logic, you can, depending on how complex your logic is, you could have a propagation delay that is vastly different than the contamination delay. So you could have a vast amount of time difference between those two, which will lead into interesting effects when we get into looking in later slides at how our timing and how fast we can run our clock. So next, let's look at the second row where we have clock going to a flop. In this case, we have basically 4 different timings that we care about. Since we only sample the value of D when clock is rising, for the most part we're just concerned with what happens relative to the clock rising edge. So the first thing that we're concerned about is the setup time. So I've said when the clock rises, it will sample the value of D, your data, and then have that send that to the output Q. Now that basically relies on D being stable at the time that you're sampling it. So there's something called the setup time, T setup, where D has to, the last time D changes has to be a certain amount of time before you try sampling it, and it has to stay stable during the time that clock is rising, because otherwise you'll get some unknown value. If you're in the middle of D changing, you don't know whether you'll get the value before it changed or after it changed if it's not stable when you're sampling it. So T setup is how much time does D need to stay stable, be there and stay stable before the clock rises. The next one is T hold. So you have a similar thing. If clock is rising and D starts changing almost immediately after the clock rises, you still might get an unknown value in the output of Q of your flop. So you need to keep D stable before the clock rises for T setup, and you need to keep it stable for a little bit after the clock rises for what's called T hold, the hold time. So you need to hold it stable and you need to set it up beforehand. So if you've done that, then when you have your clock rise, you will get an output, and that output to Q will be a sampling of D, and you will get a different, one will be your flop propagation delay, which is the longest amount of time it takes after your clock rises till you get an output, and one will be the contamination delay, the shortest amount of time it can take to get it out. And those tend to, for a flop, because you don't have all these different paths of combinational logic going through it, you just have a clock to out. The contamination delay and propagation delay tend to be a lot closer together than they do when you're going through combinational logic. Now we get to latch. Latch is probably the most complex one to examine because of the fact that we have two different edges that we care about. That is, when the clock edge rises, it opens the latch and it allows a new value of data to go through. So you can see on the diagram below, you get two things coming from the clock edge rising. One is you get an output Q that's a propagation delay. That's the longest amount of time that it takes for the Q to change based on clock rising. And one is a contamination delay, which is the shortest amount of time, the quickest that a value can come through, based on the clock edge rising. Now in this particular case, we don't have a setup and hold based on the opening of the latch, because while the opening of the latch allows a value to go through, that's not where we ultimately decide whether the latch is going to capture and hold the value. While the latch is open, potentially the data could still change in the middle of the clock being high. So we see two additional edges based on the clock or the data changing while the clock is high in the middle of its high time. So one of those edges is due to data to Q out for the basically the contamination delay, and one is propagation delay for the latest edge of data to Q out. So you can get two different times for the data to Q out changing based on, again, contamination and propagation delay. And then finally, you have the two setup and hold times, where since a latch does the final capturing of its data value based on the closing edge of the latch, so the clock falling, we need to make sure that data is not switching during the time that clock is falling. So data has to be held stable so that we get a known value is going to be held in the latch during the time that the latch is closed and the clock is low. So there's a setup time, which is, this is the last time at which data can switch before clock goes low, and so the amount of time that you have to hold your data steady before the clock goes low is your setup time, and the amount of time that you have to hold it after the clock goes low, because if you try switching the data even while you're trying to close the latch, maybe a little bit after, you still could get that data value going through. So there's a T hold time that you have to hold your data stable until after the latch is fully closed. Those are all the different timings that you have to be concerned about, and you can see it can get quite complex. So we'll go through that in a little bit more detail and how all of those times can affect how you set up your logic and how you set up your clocking in future slides. So let's go through an example of how these different delays can affect the amount of time we have available for doing our logic. So here we have an example of two flip-flops with combinational logic in between. In this, you can see we're trying to run at a given frequency of clock where the frequency is 1 over the period. The period in this case is the time from clock rising to the next clock edge rising, and that's large T that's what our period is usually in, T sub C. So that's our cycle time. Now, because we have two of the things that are set basically by the flops that you're using, so depending on the type of flop you're using, each flop will have a certain amount of setup time that's determined by just the structure of the flop and how it's clocked. So that's shown in the graph below, where you have a certain setup time that you have to keep your data has to be there and be stable by that amount of time before the clock switches. You also have a certain propagation delay from the flop on the starting side on the left going into flop 1, and so from the clock rising you have a certain amount of delay from clock rising till Q1 is available. So if we take the cycle time and subtract the setup time and the propagation delay time that are totally dependent on the flops, we're left with a propagation delay through the combinational logic, which is this is the most time that we have available for whatever combinational logic we want to put in there. If we try to put in combinational logic that takes more time than our calculated remaining propagation delay time, then we can't actually operate at that particular frequency of clock or that particular cycle time of clock. So you can see how the setup time and propagation delay time of the flops can help determine what frequency you can run at for your chip overall. Here we have a second example where we're using two-phase latches instead of instead of flops. So in this case, we have to get one cycle through two-phase latches, we have 3 latches. Latch 1 and latch 3 are phase 1 latches, and then the latch in between is a phase 2 latch. Remember, we always have to have phase 1, phase 2, phase 1, phase 2 is the way that two-phase latch design is designed to work. So in this particular case, if we look at our requirements based on a couple slides ago, we have a certain cycle time. We want to design it ideally so that the combinational logic, each phase of combinational logic together take up 1 cycle worth of time. And so we try to fit an amount of logic in both sets of combinational logic to get 1 cycle worth. And 1 cycle is from when the first latch L1 opens to the third latch L3 opens. So we have the logic going through 2 different phases. We want to make sure that we usually try to make it so that the data gets to the latch around the time that the latch is opening, so we can use the full amount of logic. It's not sitting there waiting for the latch to open, and we don't want to go too far into the latch time being open or we start running into additional problems. So we'll look at that right now. So in this case, let's say we do have the data coming in at around the time that, so D1 is coming in around the time that the latch opens for phase 1. we get a certain propagation delay through that latch, and that causes the output to come out at Q1, and the longest of that is, your propagation delay, not your contamination delay. So that uses up a certain amount of time. Then we have the propagation delay through the combinational logic 1, so that's TPD1 gets added to our delay time. And then we go through latch 2, assuming that the time to get through to D2 is after or approximately where latch 2 is open, or maybe even a little bit after latch 2 opens. Then we aren't slowed down by the clock switching because the latch is already open. So we'll go straight through that latch and get a propagation delay through latch 2, TPDQ2, and then we have the delay through combinational logic 2, so that's TPD2, propagation delay through combinational logic 2, and all that, if we get to latch 3 around the time that latch 3 is opening, then we'll just flow straight through latch 3. But you can see here, because we're trying to get through each latch around the time that the latch is opening and not trying to force our timing to get to the latch before it closes, you can see that we don't have to worry about the setup time to the closing edge of the latch. This is a way to only be dependent on the propagation delay through the latches and not be dependent on the setup time like we had with the flop. So you can see here, in this particular case, our sequencing overhead is 2 times the propagation delay through the latch, because we had latch 1 and latch 2 that we went through, and so for each cycle we only have a sequencing overhead of the propagation delay through the latch. And so this is a little bit more of a benefit over doing flop-based design, where we don't have this really high setup time, which turns out that the setup time tends to be a little bit higher than propagation delay, especially, and the other thing is the propagation delay through the latch tends to be, or could be, faster than propagation delay through the flop in some cases, if we use these inverting latches. If you go back and look at inverting latch versus non-inverting latch, we might just have basically one pass gate and one inverter to go through for an inverting latch, which can be relatively quick time delay through that. So you can see how two-phase latch design has some advantages over flop-based design as far as delay goes. So the last max delay example that we're going to look at right now is based on the pulse latches. Remember, we had said there was 3 main types of sequencing that we do: flop to flop, two-phase latch design, or pulse latch to pulse latch, because pulse latches act similar to flops in behavior. So in this case, we can see there's 2 different possibilities depending on how wide our clock pulse is compared to how long your setup time is of your data to the clock closing edge of the latch. Because we need to make sure, again, since these are latches, we're just treating them, when we say pulse latches, it just depends on what clock we're sending to them. So the data has to be set up to the closing edge of a latch to make sure that it's stable for a decent amount of time, a setup time, before the closing edge of the latch. Now, if our pulse width is long enough such that the pulse width of the clock is larger than our setup time, then we get the situation as shown in the A row there, which is our data can come in after the clock edge rises, and just flow transparently through the latch before it closes for latch L1. And so in that case, we get a propagation delay from data input to Q output. So P T sub P dq, so D to Q. And that propagation delay, after we get through that for the latch, we go through the combinational logic, and we have T propagation delay of combinational logic. And finally, when we get to the end there, we want to get to the end around the time that the clock is rising, and that would be our cycle time. And so if we can, that will determine what our cycle time is. So in this particular case, our sequencing overhead is just basically the time, propagation time through latch L1 from D to Q. Now when you look at the bottom one in the B row, if our pulse width is less than our T setup, then that means we need our data there before the rising edge of the latch opens the latch for the pulse latches for either L1 or to L2, because we're setting up to the falling edge, but since the setup time is greater than the pulse width, we need to be there before the clock rises. So this implies data is there first, clock is done after data is stable. So our propagation delay is now from clock to Q. So our starting propagation delay is T sub P CQ, clock to Q. And after Q1 is stable, then the combinational logic starts switching, and we have the propagation delay T sub PD through the combinational logic until we get to D2. And once D2 is stable, D2 needs to be stable a setup time before the falling edge, the capturing edge of latch L2. And in this particular case, since the setup time is larger than the pulse width, that means we basically need to set up before, well, normally we're talking our cycle time is to the rising edge of the latch from rising edge to rising edge. But since we get this additional time through the pulse width based on the pulse width of the latch, the total amount of time that we have is the setup time minus the pulse width. So the overall sequencing overhead in this particular case is the propagation delay of clock to Q of the first latch plus the setup time of the second latch minus the pulse width that is supplied to the second latch. So depending on the case, we take either of those two answers as our sequencing overhead for pulse latch designs. So you can see pulse latch designs can also get a little bit complex. Maybe in some cases, in some ways, they're a little bit more complex than flop design or two-phase latch design, and in other ways they're a little bit less complex than two-phase latch, but still probably more complex than flop design. And in general, the flop-to-flop type design is kind of the easiest to navigate as far as timing goes. So in the previous several foils, we've been going through what is the delays related to what we call max delay, or this is what's the maximum frequency that you can operate at, or in other words, the minimum cycle time that we can get through our combinational delays between how fast you can get the logic or the data to flow through your logic from one clock edge rising to the following cycle's clock edge rising. Now, in the next several foils, we'll be talking about min delay. This is related to just a single clock edge, and how much time it takes to get through the combinational logic, and can it go through too fast. This has nothing to do with the frequency of the clock. It just has to do with, do you allow data to go through your sequential element too fast and get to the next sequential element before it's supposed to switch. So you don't want, in this particular case, we're showing two flops, F1, whose output is Q1, going through some combinational logic to produce D2 that goes into the input to the second flop, F2. Keep in mind, when we were talking about one of the parameters for a flop input, the data input to a flop, is the data has to stay stable even after the clock edge switches high. And there's a certain amount of hold time, T hold, that the data needs to stay stable for at least that amount of time. And if it doesn't, then we could accidentally get that early data going through the flop when it wasn't supposed to. So keep in mind, even though data is coming in after the clock switches high, if it comes in too close to, even though it's after the clock switches high, if it comes in too close, it can make it through when it wasn't supposed to. So let's go through this example. If our clock goes high, we have a contamination delay from clock of F1 through to Q1, and that's the fastest the data can make it through F1. That value of Q1 goes through the combinational logic to get to D2. There's a fastest path through that combinational logic to get to D2, which is your contamination delay T sub CD of your data. And that full contamination delay of the first one through the flop and the second contamination delay through your combinational logic, that total amount of time has to be equal to or later than your hold time. And if it's not, then you could get an accidentally incorrect value going through flop 2 a cycle earlier than it was supposed to. So the equation for that is your T sub CD, or combinational delay, has to be greater than your hold time of your receiving flop minus the contamination delay clock to Q of going through the phase F1 flop. So your generating flop contamination delay clock to Q minus your hold time of your receiving flop is the amount of time that you need to have going through your combination delay to not fail this min delay check. Now let's do the same min delay analysis for two-phase latch design. So in this case we have a phase 1 latch L1 whose output is Q1. Then the delay goes through the combinational logic, goes to D2, whose input is to a phase 2 latch. In this particular case, you can see when the phase 1 latch, the clock goes high, it opens the phase 1 latch. We get a contamination delay, the fastest delay from clock to Q1 that we can get. This is followed by the delay through the combinational logic from Q1 to D2, and we want to know the contamination delay, the fastest delay through the combinational logic. So when we add those two combination or contamination delays together, that's the total contamination delay. Now again, that needs to be greater than the hold time from the phase 2 latch. But keep in mind, in this particular case, we're using, when we use a phase 1 and phase 2 clock, and we have a little bit of additional non-overlapping time where phase 2 clock going low is earlier than phase 1 clock going high, we get an additional amount of time for T hold to help us out. So in this case, we get our the time that we have available is t hold minus the contamination delay through the clock to Q minus the t non-overlap. So our hold time is actually reduced by the non-overlap time. So that helps us to actually successfully meet this min delay time for two-phase latches. Now the paradox here is we have to do that for the phase 1 to phase 2 latch. We also have to do that for the following phase 2 to phase 1 latch. So we have to do this hold time check twice for each cycle, whereas we only do it once per cycle for flops. But a flop is made of 2 latches, so you have to go through the logic to kind of make sure you understand what's going on flops versus latches and how these checks are working. Finally, let's go through min delay using our pulse latch design and the analysis. So here we have 2 latches that are both phase 1, but latch 1 and latch 2 have a pulse clock going to them. So in this particular case, we have when the first latch, latch 1, when the clock goes high, we get, as soon as clock goes high, we get a Q1 out. And that Q1 value will have a contamination delay time from clock to Q1. And then it goes through the combinational logic to D2 and has a contamination delay time through the combinational logic to D2. And you can see that there's the arc going to the earliest that D2 can change. Now, this is now compared to the closing edge of latch 2. In this particular case, you can see the closing edge of latch 2. It's clocked by the same clock as latch 1, and that closing edge depends on exactly how wide your pulse width is. So if you actually have a fairly wide pulse width latch, you can see where that closing edge could actually be getting close to that time for D2. So when we start comparing the closing edge of the latch, or the closing falling edge of the clock, T hold time, to the data propagation delay earliest D2 time, you can see that you could start potentially running into a problem there. In this case, our minimum time for the data going through the combinational logic has to be greater than T sub hold minus our contamination delay time from clock to Q plus the pulse width of the clock. So as your pulse width of your clock gets greater, you have to have more delay time through your combinational logic in order to guarantee that you won't fail this hold time check. So in this particular case, this is one of the greatest dangers of using pulse clock or pulse latch designs, is you have a pretty great danger of getting min delay problems in pulse latch designs because of this factor of the size of your pulse width increases the hold time that you have to worry about. And I've actually seen pulse latch designs that require a lot of work to try and fix issues related to this.